All right, thank you very much for being here, and thanks to the organizer for including my presentation in the program. My name is Andrea Canidio. I'm Senior Research Economist at Cloud Protocol, and what I'm going to discuss today is joint work with Vincent Dano, who should be around, and is also research that was supported by the Ethereum Foundation with the grant that we received last year. Now, I assume that there are many smart contract developers in the audience, and that is great because when working on this research, we thought a lot about you guys. In the following sense, because we were really thinking, as a smart contract developer, what can you do to prevent your users from being exposed to front-running attacks, okay? Now, we think this is a relevant question because a lot of the research that's been done recently on the topic of MEV and various types of attack has focused a lot on the infrastructure, that is, on how a transaction originates, and then, it's sent to either a public mempool or a private channel, and eventually ends up included in a block. But we think that front-running attack, MEVs, and those things also have a lot to do with how those transactions are interpreted by smart contracts once they are included in a block, okay? And so what we started thinking is, okay, can we have tools that potentially any smart contract developer could use in order to prevent their users from being exploited by attackers, okay? So let's keep the infrastructure as it is now. We can also think of the infrastructure as the one of the old day where everything was going through the public mempool. And can we work exclusively on the smart contract layer to prevent attacks? Now, I think a natural object to look at to answering this question are Commitreveal protocols, Commitreveal schemes. And in the paper, we propose a somehow novel Commitreveal scheme, which is, it's similar to a couple of things that are around. One is the submarine commitment protocol, which is in the literature. I don't think it has been actually used, and the other one is also similar to how ENS managed their domain registration. Okay, so it's not exactly the same. As you will see, there are some differences, but the novelty of the protocol is limited. What is really novel here is the type of analysis. We build a game-theoretic model of front-running, and then we use the model to study what is the effect of introducing the protocol on the probability of having an attack and the severity of attack, so on and so forth. So it's really on the methodology. And essentially we derive 3 results, which I list here in order of how intuitive they are to some extent. The first result is that this Commitreveal scheme prevents the most severe forms of front-running attacks. And I realized that this statement requires me to tell you what we mean by the severity of an attack, and this will be in a couple of slides. Then it's also, we think, interesting because it preserves legitimate competition among users. So if you want, it preserves good MEV. And again, how we distinguish between legitimate competition and attack, the formalities are in the paper, but I will give you an intuition in a couple of slides. And then the third result, that is the least intuitive, the one for which we kind of need a model to see, is that even when it does not fully eliminate attacks, the protocol is effective at reducing competition among attackers, okay? So for example, whereas with the protocol, without the protocol, you may have 3 attackers. With the Commitreveal scheme, maybe you have a single attacker. And hence, reduces total expenditure by attackers. And this also benefits the honest user. Now, of course, we know that Commitreveal schemes have costs. In particular, they require 2 messages and impose a delay. So whether, in principle, you could apply this protocol to any smart contract, but whether it's cost effective, will depend a bit on the specific environment where you're thinking about deploying it. Okay, now I mentioned the fact that we have a notion of severity of attacks, and we distinguish between honest competition and attacks. Let me give you an intuitive sense of how we define those concepts via an example, that of a smart contract that awards a very nice NFT, this one, to the very first person who can correctly answer a question. Now, let's consider 3 situations, okay? The first one is, we have 2 users, Alice and Bob. They simultaneously find the answer and they submit it. And then, of course, they realize that they are competing with each other and they will do this kind of gas replacement transaction. in order to, each of them is trying to have their transaction included earlier in the block, so to claim the NFT. This is clearly a case of legitimate competition. They both found their answer independently, and then they are competing with each other. And note that there is an element of economic efficiency here in the fact that there is competition, because this guarantees that the one who likes the NFT the most will be able to get it, because this person will be able to outspend the other guy. So the one who likes it the most gets it, and this is the efficient thing to do. Now, the case 2 is the classic attack. Alice does all the research, finds the answer, but she's naive. She sends the transaction through the public mempool. Bob is just doesn't, has not done any research, but sees the transaction by Alice and then can craft his own transaction, send it faster, and perhaps manage to steal the NFT from Alice. Okay. So this is an attack, and why it's an attack? Note that case 1 and case 2 could be observationally very similar. Like if you're looking at the mempool and the blockchain, they look the same. But clearly one is an attack because Bob is using information extracted from Alice in order to craft his own message, okay? While in the first case, this is not the case, okay? And the third case is the most subtle, which is where, we have Alice, she finds the answer and submits it. Bob is someone who was also doing his own research, okay? But he is a bit slower. So by the time Alice found the answer, Bob managed to narrow down the possible answers to 2, let's say, okay? And now he sees Alice's message in the mempool, or now he figures out which one of the 2 is the correct answer, and he can then send his own transaction, okay? Now, in the model, we classify this as an attack because Bob is using information extracted from Alice, but we will classify as a milder attack because Bob has a lot of prior information to start with, so the amount of information he is extracting from Alice is lower, okay? He's already fairly informed to start with, contrary to case 2 in which Bob has absolutely no information and is fully reliant on Alice, on the observation on Alice's message to craft his own message. Okay. So in the paper we have all the formalities, but intuitive then an attack is characterized by the fact that Bob has to use information extracted from Alice to send his transaction, and the severity has to do with kind of how much information he's relying on. So now that I told you this, I can tell you what the protocol is about. Sorry for the slide, it is a bit dense. But okay, again, the transaction and messages here are sent as they are now. This is not about infrastructure, it's about how those messages are interpreted by the smart contract. And the Commitreveal protocol does this, okay? If a honest player, or anyway, anybody, wants to send a message S to a smart contract, this player will have to first commit the message. And the commitment phase works the following way. You take your message, you concatenate it with an address that you also control, and then you hash it. And then you send this as a message to the smart contract. That's the commit message. And then comes the reveal period in which the player has to send the reveal message, and in S, so the message he intends to send, but importantly, it has to send it from the address that he committed in the commit stage. Okay, so the address that was part of the commit message. Now the smart contract received the reveal message, can observe from which address it was sent, can compute the hash, and then can check whether this message was received during the commit period. And if the answer is yes, the message is considered as valid and will trigger some action depending on the exact context. Otherwise, the message will be discarded. Okay, and of course, sending messages is costly. And there may be multiple honest users who want to interact with the same smart contract, and there may be multiple attackers. Now, note also that in the paper, so in this version of the protocol, an observer will see that someone committed something, okay? So there is this form of information leakage. We have another version of the protocol in the paper where this is also obfuscated because the commitment is placed somewhere else, and then when you reveal, you also reveal the pointer to where the commitment is placed. But even in that version, there is another form of information leakage, which is that an attacker could commit a message and then decide to send the reveal only after having observed the reveal message of the honest player. So the protocol severely limits but does not fully eliminate the ability of an attacker to act upon the observation of the victim message. in the sense that here it can still decide not to reveal reveal or not after observing the victim message. And the last observation that is important is that in this scheme, an attacker cannot clone the commit message, because the commit message, it contains the address from which the reveal will be sent. So you cannot just see a commit and copy it, because that won't work for you. You have to guess some message S that might be useful to you as an attacker in the next stage when you reveal. And hence the three main results. As I said, the protocol is built so to force an attacker to guess. And of course, again, here's the severity of the attack plays a role, because if the attacker is completely uninformed, guessing will be very costly for him, and the protocol is effective at preventing attacks. But in situations like the third case earlier, where the attacker already has a lot of prior information, it is possible that the protocol will not prevent the attacks. So we can say that the protocol is effective to preventing the most severe attacks, perhaps not on the least severe attacks. The second result is that competition between honest players is preserved. It is just pushed toward in the reveal message. Now, it doesn't matter the order in which commit messages are received, as long as they are all received in the commit period. And then when the reveal period arrives, honest players will all compete. We try to get their own reveal message earlier in the block. So essentially, competition is preserved but pushed by one period on the reveal message. And the third point, which is the least intuitive, now there is this very famous result in game theory, especially contest theory, which is called full dissipation of rent. Essentially, it says that when there are multiple competitors competing for the same price, and they are heterogeneous, at most one of those competitors, which is the strongest ex ante, can expect to earn positive profits once in the competition. And it says that everybody else expects in the competition to exert effort and pay as much as what they expect to win. Okay? And the reason is that if this wasn't the case, then the strongest player can increase a bit their effort and win also the other, and increase their payout. Anyway, just standard results. And very robust. Now, essentially, the Commitreveal protocol imposes an entry ticket, so creates an entry ticket for attackers. So the attacker has to pay the cost of the commit message to then attack. But now, you are one of the attackers, you know that once in the competition you will earn 0, why do you want to pay the commit message? So at least in the pure strategy equilibrium of the game, let's say this way, there is at most one attacker will want to pay the commit message and then attack in the following period. So this is why, even if it doesn't fully eliminate attacks, it reduces the number of attackers to at most one. Okay, so to conclude, so then the novelty here, okay, a little bit the protocol is kind of a little bit new, but particularly on the methodology of using game theory and deriving novel benefits of these Commitreveal schemes in the context of MEV and front-running attack. Note also that because it's applied to the smart contract level, it can also be very flexible. So for example, you could decide that only this protocol is required only for certain messages. So there is a set of messages that as they are received, they are executed. But then there are another set of messages that, okay, they are executed only if they were committed earlier. And it's also possible to design a system in which the scheme is required only in some periods and not in other. So it affords a lot of flexibility. That's it. So yes, these are my contacts on Twitter, and the latest version of the research paper is always available on my webpage. Let me also just use the last second to point you to the open position page at Chaos Protocol. Thank you. Finished? Okay, and questions. There is no time for questions, but I'll be also in the back if you need to talk.
I have a question I want to ask.
Okay.
No, you don't have time for questions.
Sorry. Let's go outside. I'll see you outside.